system, then we've obtained some speed up using Grover's algorithm. So the formula for matrix multiplication, we just need to construct a quantum circuit that's reversible, and there aren't entanglement issues. So it's using these Toffoli gates to compute the inner products of the vectors that are in the matrices. Are there any questions so far? Yes?
So aren't there like black box techniques to say that classical circuits and such can be replaced by quantum circuits of sort of a similar size?
There are theorems to that that say that, something very similar, but you still need to make sure that there aren't entanglement problems. Is that your question?
Yeah.
Can't every classical circuit be transferred into a quantum circuit?
Yes.
You still need to check that there aren't entanglement issues at the end, so that you can construct a reversible.
So the way that you do it, is it effective in the sense that you can compute it if I hand you a classical circuit?
Yeah, I don't know.
What?
Oh, well, he was asking, he mentioned a way to convert classical to quantum. So I was just saying, is it actually computable?
In the circuit sense, because of the universality of the set of classical gates, you can change each set of classical gates into the universal.
Oh, you just make it the corresponding quantum one?
Yeah.
Okay.
Kind of. I mean, there are sets of quantum gates that can compute each one of the universal classical gates. So then in that sense, yes, but I think you still need to check the output. And it's useful to actually compute, just because there exists a quantum algorithm doesn't mean that it's on the same order of complexity. It's good to make sure that you can compute it in the same time, in similar time.
Will the replacement sometimes make it faster? Not, or if you just naively swap it, it'll be necessarily the same speed.
It's not always faster.
If it's a reversible computation, it should be like the exact same.
Oh, it'll always be the exact same. Okay. Thanks.
So, a matrix vector product can be done in n-squared products, which is the same as classical computation. We replace all of the inner product computations with Toffoli gates. So you can see here that if we have two n-dimensional vectors, one is A and the other one is B, we can compute the inner product using the Toffoli gates and then the reverse to make the computation reversible. So for matrix multiplication, we have n-cubed Toffoli gates. This is just a naive grade school quantum matrix multiplication, nothing fancy. So, we achieve n-cubed, right, which is the upper bound for classical matrix multiplication. And we can obtain the speed up using the probabilistic algorithm and knock that down to 2. Because it's in the same time as the classical computation for matrix multiplication. And then we can quantize that and get the quantum speedup that we're looking for. So we've shown that we can do matrix multiplication reversibly and without entanglement issues. And so in terms of the complexity of the quantum computation, we can analyze, for example, a subroutine. This is a random solution, a subroutine, which takes a classical subroutine, which takes as input the Macaulay matrix, the vector R that we're looking for, the minimum polynomial, and a field extension, and outputs either false or true. Solution or there is no solution. The quantum version of this algorithm takes as input the elements of f, the coefficients of f, and so on, and outputs a boolean saying that the system is inconsistent or consistent. It also outputs the input, because that's what all of quantum circuits are supposed to do. So here's the quantum version of what the circuit is supposed to look like. You can see that it basically has the bracket notation, is the difference here. And we have a theorem which counts the number of quantum gates that are used to compute quantum random solution. And that's n cubed, plus this is the exact computation. I put the big O notation, but this is the exact number. And so we have an oracle to compute quantum random solution, which is the same complexity in the black box model as the classical computation. We can and have counted the gates for all of the other subroutines, but it's a pretty extensive algorithm when you go over all of the actual computations you need to make. So I hope you can trust me when I say that they are all similar, and that when we analyze the full consistency check, we have the same complexity. So to fully describe the quantum circuit for quantum Boolean flow, it takes as input a superposition of the Macaulay matrices. So the matrices are constructed outside, and then it takes as input the superposition of the Macaulay matrices, and outputs all of the A such that the linear system is inconsistent, because those A's are potential ends of a solution. And then it would go on to perform regular Grover with polynomial evaluation. There's a paper that does that on the remaining n minus k variables for those A's. In terms of amplitude amplification, if we have one such A, we compute the circuits for Grover on the order of 2 to the 1 minus gamma n. So it's k over 2 times. And when there's more than one such A, we compute this number of times, which is you divide it by the number of A's that you have. Are there any questions so far? And our main results are here. So this is a very similar statement as to the classical one, but as you can see, this 1 minus gamma is over 2 in the deterministic variance. And the 1 minus gamma is over 2 in a probabilistic variant. And we can use the 2 for the linear alpha constants because the complexities are similar in the black box model, or the same in the black box model. So we've done what Grover does, which is put things over 2. And for exact exponents, which is what we like, we have in the deterministic variant 2 to the 0.47 n. And in the Las Vegas variant, we have 2 to the 0.462 n quantum gates on some assumptions about the semi-regularity of the system. Yes?
Refresh my memory because I can't remember strong semi-regularity. Are higher or lower values less restrictive? So 0.17, is that requiring lots and lots of strong semi-regularity?
No.
No, okay. I didn't know which way the parameter ran.
Okay.
I didn't know which one. Okay, thank you.
Okay. This is it, the point, which is how many variables should I use when I construct my cryptographic multivariate scheme. right? When I want to think about quantum security. So, the leftmost column is the quantum security level that you desire. The middle one is the suggested number of variables if we assume that our algorithm is the best algorithm. And the third column is the standard size of a public key in a cryptographic scheme with this number of variables. So if you want 2 to the 128 bit security, you want 277 variables in your polynomial ring scheme. Yes?
I assume the middle n continues its pattern of growth. It looks like it's about a doubling.
Yeah.
Okay.
So because it's in the classical setting, you'd say, okay, well, it's double, right?
So that really doesn't bode well at all for cryptosystems based on, because if 256 bits is not a lot of security.
Yeah, it's not good. So a lot of people will say, well, for quantum security against these problems, that you as far as we know, the only tool that a quantum computer has is Grover's algorithm. You just double your key size. But it's not as straightforward as that, and a lot of people will just assume that as long as I double my key size, and I've heard the claim for other things too, that it doesn't really hold true. Yes?
It's possible that I'm misunderstanding something, but wait. How does so MQ2 is a specific problem where you're given a bunch of polynomials in some number of variables over F2, find a 0.
Mm-hmm.
And but our main interest is in cryptography, so how do you get a public key crypto system from that? Like, what's the public key, what's the private key? Is the private key like finding the zeros or something, and the public key the polynomials?
So for example, if you
Okay.
have a multivariate scheme,
Yes. So scheme is just the way you're encrypting it? Or?
yeah, so let's say that your scheme is based on this problem, right? That would mean, let's say you have a system of equations and your secret is the common zero.
Okay.
Then
So the public-
you can hide your secret by making the common zero very difficult to compute. And then only if I send a message to Delano and she knows the zeros, then she can figure out
But
the
you
common
can
zero.
encrypt with just the polynomials?
There are schemes where you can encrypt using a polynomial, right?
But
Where
using the
knowledge
zeros
of
are
the
polynomials, so-
message is equivalent to knowledge of a point in the variety, which is equivalent to knowledge of the common zero.
What's the public key part in the?
If you're doing a public key crypto system, it could be the public key could be random elements of the ideal generated by the system of equations.
Okay. And will any zero work equally well as the private key, or is there a particular one, and if you don't find this particular zero, you can't decrypt it?
So these questions are very specific to the scheme.
Mm-hmm.
Depending upon what scheme you use. I've been looking a lot into these schemes called polycracker schemes, in which
Okay.
case, yes, any zero, just as good. I don't care which zero you have.
Okay.
But there could be other schemes where maybe there are specific types of zeros that you're looking for. I can't think of one right now, but maybe.
Okay, thanks. I think I kind of missed the point that from MQ2 you could have all sorts of different encryption systems based on it. I thought there was a particular one that you had in mind that maybe, or something like that.
Because of the way that these assumptions work, you can say, okay, well, you have based your crypto system on this hard problem, but if I can solve the MQ2 problem, then I can solve your problem. It's not as direct as actually using polynomials, because you can use something else, and then I can say, okay, well, you're looking for this square in a lattice or something, right? The fundamental parallelepiped of a lattice, and I can solve the MQ2 problem, so I have some advantage in solving your problem, and there's like a reduction there.
Okay.
So sometimes it's not as straightforward as, okay, well, the public key is this set of polynomials, and then that's how you break the hash function. Are there any other questions? Our paper is currently up on archive. This is the link. We would love people to look at it, read it, comments, questions, concerns, anything really. And yeah, we're working on an extension to over fields of larger characteristics. So we're looking to work over FQ, which is also nice. It's very similar.